There we go. So that's my talk on the right or on the left, depending on how you like it. So when I was thinking about what I would talk about, I started throwing out some ideas. So we'll talk today about the distributed energy resources. How many people here are studying distributed energy resources or know a lot about them? Because maybe you could teach me something. As the professor said, the role of OSIsoft in the power industry, some other industry views, and some case studies that we have. And we'll close with a concept we call prototyping the future. Some work that's going on in San Leandro, where I'm from, San Leandro, California. So what we'll do today, I'll ask you to keep track of these three bars, right? So in any view of a system, I ask people to keep track of the raw materials of the environment, in this case the power of the electrons, the energy, so how much energy did it take to make the product you're doing, or the energy components, and lastly the information. And this is where we'll spend most of our time talking about the information components, what happens to the information, and how's that interesting. My background, I graduated from here in the late 80s as a chemical engineer. I went to work for IBM Watson Research Center. So in their research center in Yorktown Heights, New York, actually was working throughout my college career and a couple years afterwards. So some of these ideas go all the way back to the late 80s and when I was working with IBM, believe it or not. So from there I went to a consulting company, ran a major worldwide group within OSIsoft, and now this is my driveway a couple of years ago. So I think everybody notices the car on the left is a Bolt, right? You might not notice the other two cars though. The car on the far right looks like a Toyota RAV4, but it's really a electric vehicle. Right? The car in the middle looks like just a BMW 1 Series, but it's also an electric vehicle. So the one in the middle was called the Active E, and there were about 700 of them made in the country. And it was a precursor to the BMW i3. So the drivetrain that's inside the Active E that I had became the drivetrain for the BMW i3. Conversely, the drivetrain that's in the Toyota RAV4 is actually a Tesla drivetrain. So there were 700 BMWs in the country. There are 2,500, 2,400 Toyotas in the country. So I had lucky enough to drive both of those. I probably have about 100,000 miles all electric under my belt. So the company that I work for, OSIsoft, and I've worked there since 1990, has been doing Internet of Things for 35 years, and primarily in the industrial space. We really believe that this is the information that's really important, is that people with information can transform the world. People with data can transform the world. If you don't have the data, you can't measure it, you can't manage it, you can't do anything about it. So a little bit about us. We're a platform that collects sensor data in industry primarily, but also in commercial and now increasingly in consumer areas where we collect sensor data, bring it together, and run it for analytics in all of these industries. These are our major industries. Some of our industries like transportation or water or communications or data centers might be whole companies for people. Our company does business in 127 countries around the world and help out 65% of the Fortune 500 companies around the world. So it's really a widespread use of our software. I'd like to say that we touch every electron in the U.S. at least once. I'll explain why. So traditionally, we've joined these two worlds, the operational world, so what's happening in the control world, the control systems and the SCADA environment, and what happens in the IT or the information management system world. Joining those two worlds together, if you can imagine, on this side of the screen are things that go boom if you do something wrong. On this side of the screen, maybe people who want to do something wrong with those things. So we actually have a pretty big target on our back when it comes to our software and our security stance. So about a quarter of our software development actually goes into software security lifecycle. because we are the information firewall between the control systems and the outside world. So the denial of service attack that happened a couple of weeks ago was really due in part because there was no division of this. The virus was able to go right down into the cameras or into the devices that were on the internet and then come and affect the rest of the internet. So our customers really look at us in two ways: information below the line, enabling operational efficiency and operational excellence, and increasingly now information above the line. So digital transformation. How can I change the way I do business through more information and real-time information? So an example of this might be a Caterpillar truck, right, worth a couple of $1 million that you would then collect up data from this truck and enable that truck to be connected to the outside world. And now Caterpillar can sell a service to a mining customer, for example, in terms of tons of rock moved a year, not you're going to buy 5 trucks from me. Right? And in that way, they're value adding the value of that truck by taking the information and the actual physical truck, combining those together, and providing an availability of that truck, a guaranteed availability of that truck back to the customer. So in doing that, they take on the risk, and the customer doesn't have that risk. Right? So they get paid a premium for that. And we see more and more companies moving this way across the space. In big data, people talk a lot about unstructured and relational data in terms of data sets. We really focus in on the time series data and the fact that this data moves. So our system is typically employed on premise with customers, so behind their firewall because they're really concerned about security, or in a private cloud environment. And we might scale up to 20 million sensors in a single system. Not a cloud-based HPFS, but a single enterprise class system. The state of California, for example, runs their power grid on about 1.5 million sensors, collecting data every 2 seconds for 15 years. They'll run that data through their algorithms and do the predictive analysis for 5-minute, 15-minute, 1 hour, and 1 day ahead projections of what the grid's going to do. That's all driven out of our system. We don't actually do the control, but we'll do the data collection and the analysis with that. So that's a little bit of big data. So our product is really used to collect the data from everything under the sun. We have 500 different protocols that we'll collect from. We'll bring that together, bring it to the server for storage for long periods of time, and then add context and more analytics to it, and then serve that up either through our clients, third-party tools like SAP, different things like that, or if you don't see what we have, you can always write programs against it. So that's it for the commercial. One more commercial point. So this is a traditional view of the power grid, I guess you might say. We have customers in each of these bubbles. Right? So these are the major components of the power grid, from generation through the customer and the service providers in it. The reason why I say we touch every electron in the U.S. at least once is that box that's up there, the cloud that's up there in the middle, operations. There are 13 companies in the U.S. that have an operations center that control the way the grid works. We have all 13 of those companies. We also have 65% of the investor-owned utilities, some ungodly amount of the solar, and on. So when you talk DER, we get new devices. We get new distributed energy resources that are coming in and becoming part of the grid. Right? So on the far left, you have solar cells, wind, different generation sources that will be there. You get, in the middle, storage devices, whether it's flywheels or batteries or other storage devices. And on the right, you have a more set of intelligent buildings that are coming on board that can respond to the way the grid is working. So all of these issues here fall up and become part of the distributed energy resource environment, which changes the way the grid works. And what happens is you have these distributed generation sources creating the generation that actually get used at the location of the generation. They don't actually make it onto the grid. Okay? So the people who control the grid can't control these sources, right? And they don't know how to interact with them. This happens to be what's the famous duck curve. Has everybody studied the duck curve? No? A couple people? So this is the duck curve. This is, what you see here is the net load of California during a spring day, right? And what you have is 2012, so this curve was drawn in 2012 or 2013. You have the gray line is what you would see in terms of a normal day. If this was Pennsylvania, for example, you might see a curve that would start down here, go up, start peaking at 7 a.m., rise all the way up to about 2 o'clock, probably stay that way until about 5 o'clock or 6 o'clock or 8 o'clock, 9 o'clock, and then start to come down on the way out. What you're seeing here is the effect of all the solar energy within California. Okay. So all the solar is being generated and pushing down the midday net load. Okay. So if you could think about how that plays out, you have a traditional environment where you have generation sources that are generating for what used to be the peak that would probably be 3 times this that are now not being used. Right? So what's going to happen with all those generation sources? Plus, how does the grid operator know what to do when they can't see what's happening below this level? Right? Because they only get to see what's happening from the delivery standpoint. They can't see what's happening in individual buildings. Right? So we'll talk about today a lot of what's in there. So you have the IoT devices, right? So some people might actually recognize some of this stuff. So these are current transducers that are collecting data off of these wires in terms of circuits, maybe smart consumer ideas like EV chargers or light bulbs or a Nest device. And then you have other pieces like your car or your smart dishwasher, right? Throw all those together and you get a new view here, right? Which is a lot more complex and a lot more interchange that's happening between these devices. So this is a view coming back to that energy and dollars and information standpoint. We see here the new grid, right? We have distributed assets in the top left. We have the consumers in the middle, third parties and the utilities left and right. The market operators, so these are the people who are saying we're operating the grid. So they'll worry about the energy and the water and the geographic information system. They have the pricing from a regulatory standpoint, but then the locational margin of pricing down to the utility side. And so all these interconnects are becoming much more complex and need to be much more real-time, right? Because if I'm generating my solar data and a cloud runs over my solar field or my solar house, what happens? Right? I get a disruption in my generation. And all that would affect how the grid operates. And these are the people who control the grid. So this happens to be a shot of CalISO and their control room. Has anybody visited PJM or, okay? This is CalISO's control room. So each of these desks are handling a different aspect of their business, maybe a forecast for the day ahead or a forecast for the hour ahead, maybe the supply side. And what you can see, they're keeping track of weather, they're keeping track of the demand.
This is what they call the Western distribution system, isn't it?
Well,
this is Western Power.
Yeah, so this is one of the control centers for the Western interchange, yes. So this is just for California. So this represents that room that I was talking about 1.5 million streams of data every 2 seconds. So if you were trained enough, you could actually notice that the displays that are on all those walls, minus the weather ones, are actually being driven out of the OSIsoft PI system. So this is where the rubber hits the road in terms of how to keep the grid balanced and the lights on. So you get this shift from traditional, single direction generation to now there's distributed generation that's happening. This is from one of our partners, Black and Beach. All right, so a couple of case studies now that I'll go through quickly. So this happens to be some studies that were done at Carnegie Mellon around smart buildings. So I'll build up some components and then talk about them together. So what they did was start bringing together sensors. Let me back up for a second. They started bringing together sensors in this one building. So this one building here, this is their School of Art and Architecture. This is a smart lab that they had. So 1/4 of one floor of one building, they put 1,500 sensors in there, just for that one building, right? They instrumented everything down to the plug load, air quality, airflow, temperatures, the positions of these louvers, the positions of the blinds, human movements, all sorts of different things. One of the simple things that they did was they actually took data from their heating system and their cooling system and combined it together. And if you look at this graph, what you're seeing here is the energy as compared to the outside temperature. And what you're seeing here is even when it's 80 degrees outside, they're still heating the building. Even when it's 100 degrees outside, they're still heating the building. For each of these dots is an event, right? Even when it's 42 degrees outside, they're cooling the building, right? It's because the two systems never talk to each other. Right? So today you see a lot of IoT systems exhibiting just this problem, right? Your Nest thermostat originally would only go up and you'd have a slice of energy in your environment that the Nest thermostat knew about. Right? Now they started adding in other things to that, but you don't have in there your other systems that are within the home system. Right? The same thing with your Fitbit, right? You have your Fitbit collecting up an IoT stream. It gives you your health, but does it also track your other things about maybe your weight or other things? Now some of these are starting to come in and become more integrated. But in this case, just by looking and seeing this problem, they were able to retune the two systems and make it much more energy efficient by taking this middle regime here and using outside air. So they would neither heat nor cool, right? And drive that. So taking this...
It seems that use sometimes the cooling used for dehumidification.
Yeah, this could be a case as well.
Could be a case, okay.
Right. But what they did was they were really fighting against each other. Right? And you can see they have enough data here in the new regime. Right? So what they did was they took their data and they did a controlled experiment. They took one group of users and gave them no data at all. They took the next group of users and gave them visibility to information from an IoT standpoint. They gave the next group control, automation of that control, and then expert advice. Each group giving more and more information to see how they could drive change. And what they found was that in the top group, the ones who had very little or no information, they actually ended up saving 2 to 4% because they knew they were being watched. So they went and ended up changing their feedback, right? And if you just had information only, you saved about 10%. And this is something we've seen across the industries, not specific to power industry. If you give people information and they become aware of that information and care about that information, they're going to drive a 10% change in their own habits if they care about the outcome, right? Without doing any automation or expert advice. And by the time they were done, they were able to save 42% of energy in their space. They then took it from there to a commercial space in downtown Pittsburgh, where they partnered with a bank and took over 4 floors of a bank and did the same thing with very similar results. And then they took over the control systems of an industrial space at the Pittsburgh airport, and again showed similar results. Okay. So you can see a lot of the savings here is in baseline, right? Which is pretty important because you still want people to work during the day, but then there's also some savings during the day. Then they took that same philosophy and actually took it down to the Philadelphia Navy Yard. How many people went to the Navy Yard tour? A couple, right? So this is one of the buildings on the Navy Yard. Did you go to the AE hub or did you go to other places?
We went to the hub.
Okay, yeah, so the hub, this is the energy usage for the hub every day of the year against degree days, right? Every hour, every day of the year against degree days. So you can pick up that pattern. And then from single buildings, they actually went and did downtown district within Philadelphia, within Pittsburgh, and did Metro 21. And that's essentially the downtown district of Pittsburgh getting the projected and the actual environments. Another case at UC Davis, very similar, but at a campus level. So UC Davis has a lot of students and a lot of buildings. Really, the 180 buildings is what you're talking about. The 1,000 has got a lot of outbuildings. It's got an ag school to it. And so what they did was brought together all of this data. So everything from their building level utility meters, their HVAC systems, their lightings, internal and external, their water operations, their central plant for heating, cooling, and their metering on their substations. They were able to do this because we have interfaces to all these different systems. They brought it together to allow them to do cross-system analytics. And with that, they could do better operations, but they also ran things like student contests. This is a student contest for these dorms, and they showed the energy usage in the dorm in miles per hour. So what's miles per hour? Well, if you're close enough, you can read. It's miles per hour that everybody in the dorm has to ride their bicycle in order to provide enough energy to power the dorm, right? Because they want to take the units of measure and make it real for the students. Anybody know what a kilowatt is, right? But you know how fast, you know how much energy it takes to ride a bicycle 20 miles an hour, right? For 24 hours. And so they let them set their own goals and drive their results. So you could set a goal and see how well you were doing, and then they gamified it with giving you badges, and then in the end, the best dorm got an ice cream social. They take that and extend it to their whole campus. This is a campus level view. The size of the circle is the energy used in the building as collected by the system, and then you can compare and contrast your class of building against each other, and then drill down and look at the energy usage, either electrical, chilled water, steam, for a day, a month, a year, compare against outside temperature. So they use this to drive student engagement and student projects in the classroom. So they have this ready database across all of these buildings so the students can dream up whatever project they want and go after the savings that way. This happens to be one of the projects that we did with them around electric car chargers. So you see the three phases. This happens to be a three-phase high-powered charger. You can see jumps up right away when the car plugs in, goes for a period of time, and then starts to degrade over time and drive this out. So the IoT, I now have an Internet of Things, the charger, right, is making that data available. But what do you do with that data? What's the information? You need to collect it and store it, but you need to run analytics on it. So what their view was that if they could run analytics on these chargers that were not connected directly to the internet, they were only connected by their electrical sensor, they could tell how many chargers were running at any point in time on their campus. So they would know their duty cycle, right? If they have 20 chargers around campus, were 50% of them free at any point in time? Don't know, right? So what they were able to do is run what's called disaggregation. So take this signal, run it through a disaggregation algorithm to make it up into its components. And one of the things was they pull out the charger and map that into a signal, and then they could just count how many chargers were on at any one point in time. There were actually, in this load, there were 200 subloads that needed to be disaggregated. So you took a single meter, single smart meter, at a high resolution, and ran it in and made 200 more sub-meters in a virtual sense. Right? So it's this processing of the information that becomes really valuable. From that, they can derive insights, because you can't derive the insight when you're looking at 200 all lumped together. One of the things that they noticed was, when they were running their tests, was there was a pump in the garage of this parking structure that was running in the middle of the summer. And the people who were looking at the data got on the collaborative phone and said to the person who wrote the program, hey, your program's broken. It's the middle of the summer. It says the sump pump is running. Right? The guy said, I'll get back to you. A couple of days later, he got back to him and says, has anybody done a physical inspection of the sump pump? No? Well, they went and did a physical inspection of the sump pump. It turns out the sump pump had been running every 15 minutes since the last winter. In California, it doesn't rain from November to roughly November, nominally. Right? So what had happened was, we have one chemical engineer in the room. Anybody else a chemical or mechanical engineer in the room? Right? So what was happening was, the sump was filled with water. The sump pump was pumping that water out of the basin, was pumping across a head to raise it up and put it into the sewer. And then the sump would be dry, the pump would turn off, and a small valve, check valve, failed, and the water would come back down the pipe and fill the sump again. And the sump pump would turn on again and say, I got to clean this out. Right? Well, if you know anything about these kind of pumps, they're not meant to run in that kind of duty cycle. They're meant to run in emergency situations. So if they hadn't found this problem, chances are the pump would have burned itself out before the next winter, and the garage would have been flooded with hopefully only financial damage. Right? So you never know, this goes to another point, you never know what you're going to find out until you start listening to your data. Right? So although they really did this project to get access to the electric vehicle chargers, they actually paid for the whole project by saving that sump pump. Sump pump was about a $10,000 sump pump. In order to change that during an emergency situation would have been 5 times that. So they keep track of the water. We have something called a drought that we're concerned about out west. And so again, they made it into units that the students can track. In this case, swimming pools. So how many swimming pools are we saving, and what are we actually doing? So one of the things that's interesting about this is you can look across this and see that they cut back quite significantly. If this was the electrical usage across years, although the school has increased their enrollment by about 25%, their energy has actually gone down in that same time frame. One of the tools that they use to do that is their thermostat. Okay? Anybody know what a thermostat is? This is an app on a phone that they let students say, I'm hot, I'm cold. Right? Everything from I'm really cold, I'm chilly, I'm perfect, I'm warm, I'm hot. Right? So you go in a room and you can say I'm hot, I'm cold very easily, very quickly. Right? And then from there, it sends the data to the Pi system where it combines with the real-time data from the IoT devices to say what's happening in the room, right? And do we have hot spots? And you can see very easily these are the buildings we need to concentrate on. All right, so that's a little bit about a building level, a campus level. Now let's talk about an industry level example. This happens to be Alcoa, Warwick in the Midwest. What you see here is a plant that is an aluminum plant that's under pressure for change. The pressure for change was the price of aluminum is going down, 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 and the price of energy, which is a core component of what happens, is going up, up, up. So what they decided to do was create an environment where they could moment to moment decide, are we going to be an aluminum producer or are we going to play into the power grid? And at first they had a big reluctance of that. The management, the plant operators, they all said, no, we're an aluminum plant. We can't be diverting how we run the aluminum plant just because of energy. And then the corporate management said, well, you got to make more money or we're going to shut you down. Pretty quick they changed. Okay? So let me play a quick 2-minute video for you about the punchline for this from the customer.
I don't have to go out and champion pie. All I got to do is facilitate them as they are wanting to champion pie. Well, the smelter, they're saying, hey, we're not sure we're making enough production. We think MISO's taking us for energy far too much and dropping our load. So with data link, I just go in and I have a very simple spreadsheet built that I look at over the course of the day, how often was I dispatched above and below and what my incremental energy was, whether I spent more time below zero or above zero. And I put on a trend and I say, well, it looks like for the most part, you see the red line is above zero, which means MISO really takes me more for load than they do for energy. So that means I'm making my pounds, I'm making a few extra pounds, and I'm selling regulation, as well as we bid in shades, which we can not artificially, but we just reg down our tap changers, feeding power to the lines down 30 megawatts if the economics sit on our price curve. We offer spin. We can easily provide, MISO requires 10 minutes response. We can provide response easily within 10 minutes because it's just a matter of tapping the rectifiers down and pushing that energy out to the grid. All these things are help pushing us to the good side of that price curve. Financial benefits. This is the kind of stuff that corporate likes to see. When we want to go into participating in the MISO with ancillary services in the energy market, we had nothing. Okay, we're a 1960 facility. We do have a Honeywell DCS, so we do have some high tech, but that was it. We had to get an energy management system. We had to get a historian that talked to it. We had to totally redesign our pot line controls. All those costs added up to about $700,000. Metering upgrades. Now that does not include on-site resources. People like myself that worked on the project. Okay, this is just stuff that we went out and bought. When the ancillary service market opened at the beginning of the year, in 4 months, we paid off our entire bill on what it cost for us to get into the market.
So what we was talking about there is the ancillary services market, right? So the first thing we was talking about was taking for load. So the load is the load on the grid, right? So if they're asking for this much power, if you can reduce that, the power company will pay you for that reduction in your load against your need, right? And they'll do that because you essentially at that point become a virtual power plant, right? You can either make that additional power or you can reduce your load by that much, right? So in having a program where they get paid to reduce their load, that was the first part. The other part is the ancillary services. So this is stability of the grid, power quality, how that's running through. And by being able to play in that part of the environment, it's much more lucrative because it's much more fine-grained control. As he was saying, they were able to do that as well. We'll get rid of that. Get back over.
So John, can I
Yep.
ask a question there? In this case, the energy that was going to the aluminum smelter, they were able to reduce it and sell it back to the grid?
Yes. So that's, they did 3 programs. So they did a demand reduction, they did putting power onto the grid, and then they did ancillary services onto the grid. All 3. And that's where they were able to make their money. So let me see if I get back. So this is the curve he was talking about, pushing down the price curve. and this. So now one about a microgrid. So this is a Department of Energy project with the Illinois Institute of Technology, where they took their campus here and turned it into a microgrid. Microgrid is a grid, is a sub-part of the grid that can operate off of the grid, so without connection to the grid at points in time. Most of the time it stays connected to the grid, but under times of stress, maybe disaster, snowstorm, those kinds of things, they can disconnect from the grid and still keep their operation running. They do that by understanding what's happening and using their tools. This happens to be a project joint with Exelon ComEd. And here's the physical space. Running out of time a little bit, but you can see here what this does is it depicts the seven loops of energy within the campus. So what they can do is if they need to turn off the electricity on campus or turn it down, they know what are their critical buildings, what are their good buildings, and what are really nice to have buildings, right? You don't want to turn off the power to your on-campus hospital, your on-campus dorm, those kinds of things. You might shut off the gym or the swimming pool first, right? So they understand the load of all the buildings on campus, and they can control that load on campus. And under times of stress, they can make that change automatically. So they did projects around smart lighting to bring up all the lights into the PI system or their actual campus itself. One thing that they did that was very interesting in a renewal standpoint is they partnered with the International Brotherhood of Electrical Workers Union. So they had them install all the equipment on campus. So if you ever tried to do a project on campus, one of the components that you have that's a cost is the manpower to make it work. And what they did was they enlisted the union and their trade program to say, if you need a place to practice, practice on our campus. That was kind of neat. So what their microgrid controller does is it runs on 3 levels, right? So you have the second-to-second, sub-second control of level 1. You have 4-second control that's responding to how the state is operating at that point, and then economic control at the minute level for the paybacks, right? And as you work your way further up in time scale, the signals can travel longer distances to more participants in the conversation. We're running out of time, we'll blow through this. So now we'll talk about power grids versus cars. So this is again another use case of an example of a customer that makes electric chargers. So this was actually born out of a hackathon. Anybody here participated in a hackathon yet already? No? So hackathons are a place where you might go and put a bunch of creative people together with a challenge and try and solve a problem. In this case, the hackathon was co-hosted by OSIsoft and Nissan in their research labs in Silicon Valley about 2.5 years ago. And in this room were programmers, business people, people who understand energy, people who understand environment, social change. It didn't matter. You didn't need to be a programmer. And they got together and worked on problems in this hackathon. One of the problems that they came across was this idea that if you could aggregate all these car chargers together, you could dispatch them and reduce that load, much like Alcoa did. Right? And what happened was a company was born out of it. This company called eMotorworks and their juice box. So what they're trying to do is, reduce these peaks. If you reduce these peaks, you can get paid for it. And they've come up with a model that says they'll give you a discount or a fully discounted charger if you let them pick when you're going to choose to actually charge your car. So they'll run their pseudo demand response, ancillary services and demand response programs from their connected EV charger and drive that. This is where the part will drive a discussion, I hope. So I have this Internet of Things device here called the EV charger. It's telling me exactly when the car is charging and how much energy it's using. Right? So who needs to see that information? There's many different people that need to see that information. Anybody throw out a name? Who? Like what group of people might want to see it? I might want to see it as a car owner, right? That's me. Car manufacturers, thanks. You're running right down the path. Anybody else?
Grid operators.
Grid operator, they'll be in there too. Anybody else?
Research guys?
Research guys, yeah, that's good too. I didn't put them on the slide, but it's actually part of it. Others? The battery manufacturer might want to know how well the car is charging, right? This is the actual grid service aggregator or the researcher. So this is the person actually creating the algorithms to say, I can predict how much energy these groups of chargers are going to use in order to make that data available to the power company so I could get paid for telling them something they don't know. Right? Again, the information flow and the value add of that information. The power company wants to know about it, and the grid operator. Right? So each group here needs a different flavor of this information. I could care less personally about how the price of the grid is operating because I get my power at 10 cents a kilowatt no matter what. Right? I don't get to play as an individual in that larger market. Right? But if somebody's want to share with me and get me power at a lower price, maybe it's 8 cents, and give me 1 cent, that's great, right? So that's what's happening here. So the data gets collected, it gets value added through machine learning and artificial intelligence, and then gets pushed to other users in the environment.
Is there any concern about privacy?
There's always concern of privacy, but many people opt into programs for financial benefit. Right? So I'll opt in to let people know where I'm driving so I get better traffic information. Right? So in this case, the data is used for energy prediction. Right? Yes, it's called PII, personal identifiable information. From there, they can tell when you're home and when you're not and what your charging patterns are. Right? But I've trusted them as a commercial entity that's worth the risk. I can get lower cost charger, better price on my power, that they're going to really adhere to the privacy and not share my information to the outside world to tell when I'm going to be home or when I'm not. Because what happens here is when they're value adding it, they're really not telling the power company that I'm not using power. They're telling the power company that me and my 10 friends on the same power segment are not using power at that time. So in aggregate, the personalization quotient drops down. So that's an interesting case study. And so these people, the professor was talking about researchers. This was actually built from the hackathon with grant money from the Department of Energy and California Energy Commission. So this is the last case study here, and this is a company called Zip Power. So once you've built up the building, you've gone to a campus, which is all under one control. You've gone to now an industry which is a major supplier, a major consumer, again under single control. We've talked about electric chargers for cars, which is many people but very small, with one type of distributed energy resource. How do we really affect a larger change in a community? And California Energy Commission posed this question in a grant last year. This happens to be one of the companies that we're partnering with around this. The idea here is, the question is, how do you take a whole community that's using power in a traditional way and move them entirely into a distributed energy resource, cooperative processing, and cooperative engagement environment? because, you know, if I could just change one car charger, it doesn't make a big difference. But if I have a whole set of buildings within a township, now that whole load on that township can be adjusted and play into how the grid works. Right? So they have a mantra that's in their business model that they actually proposed. It was a strike of lightning for them. The call for the grant came out just as they formed their company. And they literally just took their business plan, put it in a grant, and shipped it to the state of California. So their business plan is to engage the community, to educate them about this whole problem, about how they can get distributed energy resources, solar and battery, in their commercial buildings to make the change. They'll help them upgrade through this process. This actually happens to be a net zero building within San Leandro, where we're from, and where the pilot site is for this company. This whole building is a retrofit, net zero. You see it's got a lot of solar cells. It's also got some wind. This happens to be where they train the electrical workers again. So there's a little bit of a demonstration here. These pair of cells track. The other ones are fixed. But they have passive cooling in the building to open up windows at the right times and take cool in the air at the bottom and let hot air out at the top. They have heat swapping from the hot side of the building to the cool side of the building. So all in all, this building has been net zero as a retrofit for 2 years now. But that's the upgrade component. Then they want to connect all these devices, connect the batteries, the solar, and the building together into their brain center. And once you have the data from all these IoT devices in the brain center, now you need to run machine learning on that to extract more information. What's the predicted load? What's the predicted needs? What's happening in the outside? And drive the change. And then from there, they can aggregate that up on a district-by-district basis and share that with the power company. So this happens to be a project that's got the city of San Leandro in as a participant, our company OSIsoft as the infrastructure, the company doing the real work, Zip Power, PG&E, the local power company, and CalISO, the grid operators, are all partnering in this grant. Lastly, I'll close with how all this affects an innovation space. So about 8 years ago, our founder founded a second company called San Leandro. We want to have fiber and communications infrastructure brought into our building, and Comcast and AT&T and all the big players wouldn't do it. Why? Because it wasn't economically feasible. Right? San Leandro was traditionally a manufacturing economy. We had a Dodge plant, was the home of Caterpillar, where Caterpillar started. We had a Del Monte canning factory, sit between a port and 2 rail lines. All of this is around heavy industrial. Don't need to tell you people what that's like, right? And there was really not a lot of economic activity in the town. So our founder put in a few $1 million of his own money and created a company called San Leandro and formed a partnership with the city to pull fiber through the public conduit and light up fiber throughout the city to all the commercial space. As part of the deal, he lit up every public building, lit up every school, and then allowed the other commercial buildings to come on board. And what's happened in San Leandro is now there's been a rebirth. There's companies that create 3D printers. There's companies that actually create the designs that will work on 3D printers. There's companies that do massive scale-out printing for like 100 3D printing at a time and shipping those. Right? So there's a whole 3D printing enclave within San Leandro. Actually, in this old Dodge factory is where they're located. All those companies, there's about 6 companies in that one space. Then there's an animation company that works with Pixar. There's other companies in IT space besides ourselves that are coming in, companies like Zip Power. This happens to be our new building. So this building is going to be a smart building. On this parking structure, we're going to have our solar cells and our batteries. And on this building, it'll be smart and interact with the energy supply that's here. But this isn't something that just kind of happens automatically. You got to think it through. So the regulations of how you share power actually have to do with the meters on the side of the building, right? So the way the place was originally designed, there was a power meter on the parking structure and a power meter on the building. An average approach to a campus problem like this. The trouble is, if you put the power meter on the parking structure and all the generation on the parking structure, then you sell the power to the power company through the meter before it can come back in around the corner into the user of the building. Right? So we have to actually put our own distribution network in between the two buildings. And eventually the site is going to have 5 buildings, so they have plans to have a much larger interaction. The other thing that happened was we got a 55-foot tall statue in front of our building. That was at Burning Man, so helps drive a lot of innovation. So we've had tourist groups come from Switzerland, Austria, Germany, Korea to look at the statue, but also talk about the energy dynamics of our city. Right? So it's kind of interesting how art breeds innovation. A summary slide about the opportunities when you start looking at all of this information and the different players. I'll leave this for you so we can have some questions. Sources. By all means, shoot me an email if you want. Here's places to go look up things. Our website is a huge resource. We have a search box. Just put in any question you might want or a company name, and you'll get a list of presentations. We have about 1,200 customer presentations up there, all sorts of different IoT, industrial IoT use cases. These are some search terms. So CEC, EPIC, DOE, RPE, those are 2 grants that we've been pretty prolific in. Prototyping the Future is a conference that generated that zip power company as an example. I hope that I was able to give you a great view about how energy and information come together to drive economic change. The thing that is there to talk about is the IoT device is just a device. The information that comes off of it is where the value add starts to come. Right? All the machine learning, all the analytics, because that's what people further down the supply chain are going to pay for. Otherwise, you're just paying for the device. That car charger, average car charger might be $450 if I just give you a car charger and you pay me money. The other view of that car charger is it's worth about $3,000 a year in value in California. Your mileage may vary. So when you start value adding, you get a lot more money to play with. So follow the raw materials, follow the information, then you'll follow the money. Questions?
Round of applause.